Hi, I'm Prastika Jiwanti, an assistant professor at the Faculty of Advanced Technology and Multidiscipline, Universitas Airlangga. I'm thrilled to have you here for an exciting journey into a world of healthcare innovation in screen printing electrodes for point-of-care diagnostics. We've been hard at work delving into a groundbreaking area of research in screen printing electrodes that has the potential for point-of-care diagnostic. Now, you might be wondering, what's the big deal about screen printed electrodes? Well, hold on tight, because we're about to unlock the door to a realm of possibilities that could innovate how we diagnose and treat diseases, especially in point-of-care settings. These electrodes serve as the backbone of a new generation of diagnostic tools, offering speed, affordability, and portability, all critical factors to build a sensor device. Imagine a future where medical diagnostics are not confined to the lab, but are accessible wherever they are needed most. All right, let's get into how we fabricate the screen-printed electrodes and see what we've done with the application of the screen-printed electrode itself.
I'm working mostly on electrochemistry using carbon-based material, for example, diamond material, classic carbon, graphene, and then fabricated into screen-printed electrode. And we are already working with this with several applications. And the first one is for biosensor and medical sensor that we're going to talk in this video. And the second is for environment, and the last is for energy and product. And for biosensor and medical sensor, we mostly now current project we're working with antibiotic sensor, artificial sweetener sensor, pharmaceutical sensor, and medical sensor. And for environment, we're also working with heavy metal sensor, and also now we are starting to work with pollutant degradations. And the last, in energy sector, we are working with CO2 electrochemical reductions. So before I proceed with the applications of the screen printed electrode itself, I'd like to introduce one material that we mostly use in our lab. This is a boron diamond material. We use this as an electrode. The PDD electrode is synthesized in MPACVD, microwave plasma acid chemical vapor deposition. And then in here, we deposit the boron on the boron inside the diamond structure, and then we deposit on the surface of a silicon wafer. And then this is boron diamond electrode and an image of the surface of the PDD electrode. And then we use this for the application of electrochemical applications. This is the boron diamond. The special thing about boron diamond is that it has a wide potential window, low background current, and high stability compared to another electrode. For example, classic carbon electrode, and then another metal electrode, for example, gold, platinum, and other metal electrodes. So this is very important for sensor applications since it has a low background current. So you will have a very low limit of detection compared to another electrode, which has a higher background current. So that's the principle. And beside the polycrystalline boron diamond, we have a nano size of boron diamond, which we call is a boron nanoparticles or boron nanopowder, which the size is around the range of 0 until 2050 nanometers, and we can make it in another size as well. And then we fabricate these nanomaterials, this boron nanomaterial, as a screen printed electrode. Okay, so the first application that we'd like to introduce to you is sensitive and selective electrochemical sensor for antimony using a boron diamond nanoparticles. So it's a collaborative work between us here and also some collaborators from Malaysia. Okay, so basically this is the photograph of electrochemical cell where we put the screen printed electrode here in the connector, and then we connect with potentiostat. And this one is the characterization. The left, in the right side is the SEM image, and then the XRD characterization and FTIR, and also UV phase of the boron diamond nanoparticles. So what is SPE? As we already studied in the video, as you can see here, the SPE is contained of 3 electrodes here. There's a counter electrode, a working electrode, and a reference electrode. So, and then it's connected with the dielectric polymer here. So that, and then connected here, connected with the silver nanoparticles. And in here, there's a dielectric polymer. So the analysis is only in here. So basically, the screen printed is like that. Okay, so mostly what we modify here is only on the surface of a working electrode. Okay, so this is a screen printed carbon electrode. The S per B or signal per background when we analyze the antimony on the surface of a screen printed carbon electrode, and we compare this with the screen printed carbon electrode that is modified with boron diamond nanoparticles. As we can see here, the signal per background. So this is this is the background and this is the signal. So the difference is quite a lot when we use the modified boron dipole nanoparticles. Signal per background ratio is higher compared to when we only use conventional carbon electrode. So this is why, because boron dipole nanoparticles has a lower background current, so the background current is quite low. So that's why the signal is higher when we are using a boron diamond nanoparticles. So it may provides a better sensitivity at the same concentration. And then we tried to determine the limit of detection when we are using the screen printed diamond electrode. So with the various concentrations, we have a linear calibration in here. And then finally, we can get the limit of detection in nanomolar. So about 24.1 nanomolar. So it's pretty low, and we can analyze a very, very low concentrations of antimony in environment. So we use here the square wave of voltamogram with the 0.39 micromolar antimony in 0.1 molar acetate buffer, pH 4.5, using screen printed electrode modified with boron dipole nanoparticles. We can get a very low limit of detection. Compared to the previous study, for example, when using gold nanoparticles and then the screen printed electrode modified with mercury, and also glassy carbon modified with reduced graphene oxide, we still have a comparable result in here, where we can get 2.49 or 24.1 nanomolar. So it's pretty low. And then we try also the selectivity. So we try with a different other metal, for example, with cadmium, and then with lead, and then Fe, and also cobalt, and we can get a very good selectivity, and those metals doesn't interfere in the signal of antimony itself. And we try in the real sample, which is in the river water, and we can get a very nice recovery in here, and also reproducibility. So it's very good. We can have a very sensitive and selective electrochemical sensor using a boron nanoparticles modified or fabricated as a screen printed electrode. Okay, and the second application here is we fabricate and also characterize the nanocomposite of reduced graphene oxide as an O2, and we use this for electrochemical sensor of ciprofloxacin. So why ciprofloxacin? Because as we know that antibiotics is antibacterial agents that against most aerobic gram-positive and gram-negative organisms. So it's mostly used by humans, as well as it is given to animals to prevent any infections in animals. But a lot of antibiotics are given to animals. That's why it contaminates the food, for example, like milk, and also fish, and also meat from chicken and cow, and etc. So that's why it may cause a heart problem, abdominal discomfort, tendon rupture, and bacterial resistance. If it is consumed too much. That's why we would like to make such kind of detection tools to monitor the concentration of antibiotic on those foods, as well as in humans. So this is the design. So we have a screen printed electrode here, and then we have a connector in here. This is S.Si and its connector, and the system is connected to IoT, which is we can analyze in phone like this. So you can get the direct quantitative and also qualitative analysis. Okay, so this is the send image and also EDX characterization. When we can get in here is screen printed electrode modified with graphene oxide. We got this concentration of oxygen, and then when we reduce, we have reduced graphene oxide. The concentration of oxygen is lower in here, and then we modified this with tin, and we can get EDX characterization here thin. So it's concluded that we succeed to modify this material on the surface of screen printed electrode. And this is the XPS characterization that prove also the presence of a tinned oxide and so on the surface of a screen printed electrode. And the TEM analysis we also did, and we get the size of a thin oxide nanoparticle, which is about 3.3 nanometer. So it's very, very small, actually, but the lattice distance of a graphene oxide is about 0.171. So this is the TEM image. And also we analyze using signal per background value. When we compare by using only reduced graphene oxide and also reduced graphene oxide already composite with a thin oxide, and we get also a higher signal per background compared to when we only use a reduced graphene oxide. So the presence of thin oxide may improve the sensitivity or the signal values of the ciprofloxacin itself. Okay, and we try also to compare the limit of detection and also sensitivity. And we can get the limit of detection when we're using tinned oxide composite with a reduced graphene oxide. We can get a very lower, about 3 times lower, and also as well as the sensitivity, we can get 3 times higher when we modify the screen printed electrode with the RGOS and O2. And then we compare with the previous study using various electrode. Our work in here can get about 2.03 micromolar. Compared to another, it's about 6 and 2 and so on. So it's our electrode is comparable to the previous, even better to the previous study of ciprofloxacin sensor in different modified electrodes. Okay, so we try here to analyze in milk and also in river water. And we found here the good recovery here and also good reproducibility, both in milk and also in river water. So it's our analysis is accurate in here. And then we analyze also the voltammogram of ciprofloxacin in the presence of chip. So this is the voltammograms, yeah, in the presence of ciprofloxacin and the absence of ciprofloxacin, and we can get a very clear signal. Yeah, it's very good signal in here. We can analyze like this. Okay, so those I can show you 2 applications. If you want to know more, we can have more discussions in SEGTA 2024 in FTM Universitas Erlangga. So thank you all for all the collaborators and also the team here in Universitas Erlangga.
Thank you for joining us on this fascinating exploration into the world of screen printing electrodes for point-of-care diagnostic. Stay curious and stay inspired. This is Prastika signing off. Take care and see you at SEGTA 2024 at FTM Universitas Erlangga. See you.